Hi everyone, Dusty here from Discovery Lab in Tulsa, Oklahoma for Discover at Home, a series of experiments and activities that you all can do with a parent or caregiver in your own home. Our experiment for today is Shiny Science, where we'll be learning about oxidation and chemical changes. For our experiment, you'll need a few things. You'll want some pennies. Try and find ones that are a little brown, not the brand new ones. Some paper towels, a container to mix in, a stir stick or a spoon, some salt, and some vinegar. Before we get started, let's talk a little bit about chemical and physical changes. Whenever we do science, we can classify changes in one of two ways: a chemical change or a physical change. In a physical change, the molecules or the pieces that make up an item don't change. They stay the same. For instance, this piece of paper right here. If I grab it and I rip it in half, and I have two pieces of paper, but the molecules of paper are still the same. Also, I can take this and tape it back together. I could fix it and make this new. And the last way we know it's a physical change is that we didn't make anything new. I still just have paper. I haven't made a new material. So, the molecules that make up this paper have stayed the same. I haven't made any new molecules, and I could fix it or reverse it. Another example would be ice melting. If you get a glass of ice and let it melt, it turns into water, right? But if you take that water and put it back in the freezer, it'll turn right back to ice. That's an example of a physical change. Let's talk about chemical changes now. Got the same piece of paper I had before, but let's suppose something else happened to it. Instead of it getting ripped, let's suppose it caught on fire. What do you think would happen? Would I still have the same molecules of paper? Would I have something different? Would I be able to fix this paper? Let's see. So you can see that my paper begins to ignite and burn. We've got flames coming out of it, as well as a little bit of smoke coming up in the air. Also, my paper is changing. It's not paper anymore, it's more of a gray ash. So the molecules that made up my paper have turned into fire, which is light and heat, smoke, and then ashes. So I've completely changed the molecules inside of this. So a little bit left right there that stayed paper, but everything else has had a chemical change. The chemicals inside of it have been completely broken apart and made into new things. Let's take a look at our pennies. If you ever looked at a handful of pennies, you might notice that some of them are much shinier or newer looking than others. Now, this isn't always because they're brand new. It's because they're not oxidized. Whenever a penny gets oxidized, that means that oxygen has bonded with the copper on the penny. So if you take a look at this guy right here, you can see that they're much browner or darker than this guy right here. These are more oxidized. That means that the copper that covers this penny has bonded or stuck together with oxygen. So the molecules on the top of this penny are now different because they've got oxygen stuck to them. You might have seen something similar if you've ever seen rust. Rust is an example of oxidation, where oxygen bonds with iron. Iron is found in a lot of different things, like steel. So if you've ever seen something that looks rusty, that's an example of oxidation, or oxygen sticking to the molecules of iron and making something new. Those pieces that are rusty, they can't go back to being iron without a lot of work. We can't just glue them back together. So that's an example of a chemical change that's taken place. But I'm going to show you a different chemical change we can do to take my pennies from dull back to shiny. Grab your container that you're going to do your experiment in. You could do this in a bowl or any small dish, but you want to make certain that it's going to hold a good amount of liquid and you can stir it without it making a mess. Pour about a teaspoon of salt in the bottom of your container. Then pour about a 1/4 cup of vinegar over the top. Now, don't worry if you don't get it exactly right. This will work as long as you have enough salt in your vinegar. What we're making is an example of a pickle, which, if you probably guessed, this is the same stuff that they would use to make pickles, vinegar and salt. They make a lot of different changes in vegetables when we put them inside them to make them pickled. So this is going to do something fun to our pennies. So let's stir this up. What I'm doing now is I'm dissolving my salt in my vinegar. That means that all the crystals, or little pieces of salt, are getting made smaller and smaller and smaller until the molecules of them kind of stick between the molecules of my vinegar. Now, vinegar, believe it or not, is mostly water. And that water is really good at dissolving things. If you've ever been in the ocean, you've seen salt water. That's water, it just has a lot of salt dissolved in it. When we're making a solution, we have two different things. I've got my solute, which is a thing that's dissolved, salt in this case, and my solvent, which is a thing that does the dissolving, water in this case. So my solvent of vinegar, which is mostly water, has been dissolving my solute into it. Now you can see that my water has gone almost perfectly clear. That shows me that all the salt has been dissolved completely. So that way it's mixed all the way throughout very, very regularly. There's not any big salty spots. It's all the same all throughout. We call that a homogeneous mixture if it's all the same all the way throughout. Now it's time to put our pennies in. Pick a penny that has a good amount of that oxidation, that brownness on it. Drop it in. I'm going to do a cup. And I'm going to save one to the side that's still oxidized so we can really see the difference. Use your stir stick to kind of swirl them around a bit. Now, what's happening is, remember I said oxygen was bonded or stuck to those molecules? Well, this is going to help strip off some of those molecules. So it's actually kind of peeling back a little bit of my penny. I'm actually taking just a couple of thin layers off of it. But if I can grab this guy with my stir stick, or you can use your fingers if you don't mind them smelling a little bit salty and vinegary, and you don't have any cuts on your finger, you can pull them out. And now take a look. Can you guys see the difference in color between these guys and that guy right there? These guys have gotten way less dark. I've peeled back a lot of the oxidation from this guy. He still looks really dark and oxidized, whereas these guys look shinier and brighter. But you notice they don't look exactly like a new penny. They look more orangish. That's because, believe it or not, what I've done here is I have stripped off a couple of molecules, but they have started bonding together with some different ones. The salt that's inside this is made up of two different things, sodium and chlorine. We call this sodium chloride. That's what regular table salt's made out of. Whenever you have chlorine and copper, they mix together to make a different type of chemical. They're going to make something that's called malachite. That's, if you've ever seen the Statue of Liberty, how she's kind of greenish, that's why she's so green. She has malachite all over her. She is made of copper. But whenever the salty seawater comes and splashes against her, all of the chlorine inside the salt actually mixes together with the copper. Now the fun thing about this is it makes kind of a protective skin on top of her. If we cleaned the Statue of Liberty every single year, we just scrape off molecules and molecules of copper until eventually she'd be paper thin. Matter of fact, we used to clean her a lot until we started wearing holes in her. So we think she looks all right green and we don't want to tear her up. So that's why we have a green Statue of Liberty. I'm going to let these guys sit for a bit and we'll be able to see that malachite growth here in a little bit. So if you take a look right here, I've got my row of cleaned pennies and my row of uncleaned pennies. Take a look at these two guys right here. These were both the same color whenever we started, but you can see how much darker this guy is. He's still got all that oxidation over the top of him. This one, we scrubbed off a lot of the oxidation, but you can also see that it's not the same color as a brand new penny. Like I said, we've actually mixed this up with a little bit of chlorine, and so it has this more orangish color. Now take a look at some of my newer pennies right here, and you can see the difference between them is still pretty cool. They have been cleaned and a lot brighter, whereas these guys, you can tell, a little bit duller or darker. That's that oxidation I was talking about. Now, if you look real closely, you might see some little black spots right here. This is another really cool thing that's happening. This is an example of sulfur binding with it. Now, if you've ever smelled rotten eggs, you've smelled sulfur. Sulfur is also what makes the smell of matches. So this has happened because there's actually sulfur particles on your skin. It's what makes you smell bad when you get real sweaty. So everyone has a little bit of those on our skin. So that sulfur then combines with a lot of things to make this really, really black dark spots. So that's not oxidation. But this right here is oxidation, where it's just gotten a little bit kind of brownish or a little bit dull. But these black spots, totally different. But still, you guys can see the difference between our cleaned pennies and our still oxidized ones. So it might be a little hard to see, but we're getting some of that malachite forming right here. So if you look right here, we've got two little dots of green right there starting to grow up right there. And if we look over here, this one's got a little spot right here by his ear, another part right here. This one's getting a little bit of around the edge. This one's got just a dab of it right there. And this one, I can see just the barest bit of it starting right there. Now remember, whenever the Statue of Liberty started turning green, that's because she was left out for days. If you wanted to do this even better, what you could do is you could take your pennies and soak them inside that vinegar and salt for longer. Remember, whenever you do that, it's ripping off some molecules of copper. There's actually copper inside your pickle, your vinegar salt mixture. That mixes with the chlorine from the salt to make the malachite. So the more pennies you drop in there and clean, the stronger your solution is going to be at making malachite. Mine only cleaned a couple of them, so there wasn't a ton of copper dissolved inside of that. But if you all took a whole handful of pennies and kept cleaning them, eventually you'd have enough that you could turn about 100 or so pennies, all that fun greenish color all over. So that's a fun experiment that I think you guys could try. How many pennies does it take to turn one of them all green? If you let them sit overnight as well, so that way they can really dry. Don't dry them off. Let that kind of liquid sit on there. And it almost looks kind of like crystals growing on it. So that is an example right there of some malachite growth that we see after cleaning our pennies with our vinegar and salt solution. So hopefully you guys have enjoyed learning about chemical changes and oxidation with me. Remember, oxidation is whenever one element or type of atom mixes with oxygen, which is in the air. And remember, that was the brownishness on your pennies and it's rust. And then we talked about a couple other things. Whenever our copper mixes with chlorine, it makes greenish malachite. So you can see that all the different elements work together to make different molecules and make new things. Because even though regular copper is all this shiny kind of orangish, malachite, which still is copper, turns green. So have fun doing this experiment, and I'll see you guys later. Thanks so much for hanging out, guys.